Welcome to watch my presentation. I'm Shidong Liang, come from the Yat-sen University in Guangzhou, and I will talk about what I did in my research. And my research actually involved several fields. And first is the theoretical condensed matter physics. And I only talk about the field emission theory, and then I moved to the theoretical physics, which involved the quantum physics. And in particular, I talk about the topological state, geometry phase, and also the long-commutative quantum mechanics. And I will briefly talk about the gravity and cosmology, and also my two recent paper on the fringe geometry application in physics. But I think I do not have enough time to talk about the detail of all this field. But anyway, you can find all of my papers from this link. And totally, I published papers are 85, and my current H index is 19. And let's talk about the field emission theory. I developed a computational framework of the field emission theory for the nanomaterial. But most important result is that I generalize the Frolohom theory of the field emission for the carbon nanotube. And based on this paper, I published a homograph on this topic in the 2014. That's what I did in the field emission. And let's move to the other topic on the quantum mechanics. I propose some new concept to characterize the topological invariant, and which include the global barrier phase, the complex energy plane, and the velocity field. And more interesting is that I find the complex barrier curvature is related to the quantum Hall emittance. Quantum Hall emittance is a generalization of the quantum Hall conductance. That's the new theoretical prediction in the long Hamilton system. So that's what I did in the quantum physics. And in the gravity and cosmology, and I generalize the Einstein general relativity to the wire geometry formulation and its application in cosmology. And that's what I did in the gravity and cosmology. And this formulation can be used to understand the dark matter and dark energy. But here I don't have enough time to talk about the detail of this theory. And here I also added a special issue with my collaborator, and that's the paper correction. And recently, I also published two papers on the physical geometry application in physics. One is related to the quantum mechanics, and the other is on the Einstein general relativity. But here I also don't talk the detail about these two papers, and then I will talk about what I did in the non-commutative quantum mechanics. And here is a journal paper I published recently. And what is the non-commutative quantum mechanics? The key point is I generalize the Heisenberg commutation relation to the non-commutative relation. And you can see here the xi at xj and pi pj are also non-commutative. And so the commutative relation in the phase space can be explained as the free matrix in terms of the two parameters theta and eta. And the key point here, we propose a non-canonical map to transfer the non-commutative relation to the Heisenberg commutation relations. And that's called the Heisenberg representation of the non-commutative quantum mechanics. But here we cannot talk about the detailed this formulation because the time limit. But basically, the non-commutative effect can be explained the effective gauge potential, and then we can obtain the generalize the Schrödinger equation with the non-commutative effect. And also we can obtain the Pauli equation with the non-commutative effect. And here the A is the normal magnetic potential, and A at the is the effective gauge potential. And you can find the detail in this paper. And we can also update the Craig-Gordon equation and Dirac equation with the non-commutative effect. And what is the physical meaning of the non-commutative quantum mechanics? Here, the key point we can endure the non-commutative parameter with the Planck length and cosmological constant, and such that the non-commutative effect can be explained as the Planck constant and cosmological constant. So the non-commutative matrix can be also explained in terms of the Planck length and cosmological constant. And here you can find the detail from this paper. And we may ask what normal physics happen in the non-commutative phase space. And we find intrinsic velocity appear from the Schrödinger equation, Craig-Gordon equation, and Dirac equation. They have the similar form, but here, but they depend on the local coordinate system. And similarly, we also find a symmetry, intrinsic acceleration from the Schrödinger equation. Here, I also cannot talk about the detail of this story. But more interesting is that for the Dirac equation, and using the perturbation approach, we solve the Dirac restriction and obtain the ground state energy, and we find the energy gap is a symmetry, and which implies the particle antiparticle is a symmetry, and that energy gap depends on the cosmology constant. This is the fundamental problem in quantum mechanics. And based on this energy gap asymmetry, we can also depends on the quantum decoherence time based on the uncertain principle, and the quantum decoherence time also depends on the cosmology constant. So that's why we observe the particle much more than antiparticle in nature, and also why the quantum decoherence time very quickly, because it depends on the cosmology constant. The cosmology constant is very small, So that's the main result what I obtained from the non-commutative quantum mechanics. And you can find the detail in this paper. And summary, I published paper about 85, and my current H index is 19. And you can find all of my papers from this link. And that's all what I did in my research. Thank you for your attention.